All right, let's dive into one of the most brilliant logic puzzles out there. It's a high-stakes problem for a king who has 1,000 bottles of wine, a little bit of poison, and a very tough decision to make. And I promise you, the solution's going to make you look at information in a totally new light.
So here is the challenge laid out for you. 1,000 bottles of wine. Beautiful, right? Except one, just one, is poisoned. Now, you've got 10 prisoners to help you figure out which one it is. But here's the killer constraint. You only get one shot, a single round of tasting, to find the deadly bottle. How on earth is that even possible?
Okay, so let's get the rules crystal clear because every single one of them matters. We've got 1,000 bottles, and we know for a fact only one has poison. We've got 10 prisoners available for testing. If a prisoner sips even a tiny drop of the poison, they will die. And the biggest rule of all, you can't test, wait for the result, and then test again. All the tasting has to happen at the exact same time. So, what do you do?
Well, the big breakthrough, the real aha moment, comes when you stop thinking of the prisoners as just simple testers. You have to realize that their ultimate fate, whether they live or die, isn't just a tragic outcome. It's a piece of data. Together, they're about to send us a very, very specific message.
You know, the first idea that pops into most people's heads is, okay, let's just have each prisoner test 100 bottles. But that's a total dead end. Think about it. If one of them dies, all you know is that the poison is in their group of 100. That's not nearly specific enough. We need a system where any outcome points to one single bottle.
So what if we flip this on its head? What if the specific combination of who lives and who dies could be a kind of code, you know? A pattern where prisoner 1 dying and prisoner 2 living means something totally different than if they both died or if they both lived. Each unique pattern of death could act like a unique signature, pointing directly to the poisoned bottle.
And the perfect system for creating that code is one of the most basic, fundamental ideas in all of computing: binary. All we have to do is decide that alive equals a 0 and dead equals a 1. That's it. That is the entire key to unlocking this whole puzzle.
Now, this is probably where you might be scratching your head. How can just 10 people give us enough unique combinations to identify one bottle out of 1,000? It doesn't feel like there's enough information there to work with, but trust me, there is.
Because here's the thing. 10 prisoners don't give you 10 possible answers. They give you 1,024.
Let's quickly break down that math, because it's actually really simple and really powerful. Each prisoner has only 2 possible states, right? Alive or dead. So, with 10 prisoners, the number of unique combinations is 2 to the power of 10, which is 1,024. That's more than enough unique signatures to assign one to every single one of our 1,000 bottles.
So here's the actual strategy step by step. First, you number every single bottle, 1 through 1,000. Easy enough. Then, you take each of those numbers and convert it to its 10-digit binary form. Next, you assign each of the 10 prisoners to a position, or a bit, from 1 to 10. And here's the final rule. A prisoner only takes a drink from a bottle if their assigned position has a 1 in that bottle's binary number.
Okay, so the test is over. The tasting has happened. Now comes the grim part, but also the incredibly elegant part. All we have to do now is read the result. We're not just looking at the outcome, we are decoding the message that it spells out for us.
Let's use a real example to make this super clear. Let's say bottle number 1,000 was the poisoned one. The binary for 1,000 is 1111101000. Now, based on our rule, any prisoner whose position corresponds to a 1 has to drink. So prisoners 10, 9, 8, 7, 6, and 4 all take a sip. If bottle 1,000 is poisoned, this is exactly the pattern of who lives and who dies that we'll see.
And this brings us to the final, beautiful step of the code. We just translate the status of each prisoner back into a binary digit. It's a simple one-to-one mapping. If a prisoner is dead, we write down a 1. If they're alive, we write down a 0.
So if we applied that logic to our example, we just read the results straight down the line, from prisoner 10 to prisoner 1. The pattern of who's alive and who's dead gives us this 10-digit binary number. 1, 1, 1, 1, 1, 0, 1, 0, 0, 0.
And here it is, the punchline. You take that binary number that was written by the fate of the prisoners, you convert it back to a normal, everyday decimal number, and what do you get? You get 1,000, the exact number of the poison bottle. The pattern of death literally is the bottle number. It's just perfect. What is so cool about this is that it's not just some clever trick for a brain teaser. This whole method of using binary outcomes to find one unique item in a huge group, it's a fundamental principle in computer science and information theory.
This idea actually has a name. It's called binary indexing. It's just a powerful way of using a small number of tests that have only two outcomes, like yes, no, on, off, or well, live, die, to find one specific thing in a massive group with incredible efficiency.
And I promise, once you get this pattern, you are going to start seeing it everywhere. It works for bottles and prisoners, sure, but the same logic applies to finding a faulty server among thousands, or testing batches of medicine. The math is always the same. 2 to the power of your number of testers tells you the maximum number of items you can check in just one go.
So the next time you hear a problem like this one, you're not going to be stumped. Someone asks you, hey, I've got 500 items and 9 testers. Can I find the one bad one in a single round? Well, now you know exactly what to do. You just ask yourself, what's 2 to the power of 9? It's 512. And since 512 is more than 500, the answer is a confident yes. You can absolutely find it. Now you know how.